let's go ahead and take a look at this briefly, and we'll kind of walk through it. And I want to talk a little bit more about one part of it. We'll try and do it somewhat quickly here. And where am I? Yeah, cool. So let me grab this one page here real quick. Sorry, 1 second. So, oh yeah, where'd my other? Sorry, I've got notes all over the place as typical. And I'm losing my. There we go. Okay, cool. So, fundamental theorem of calculus. Making the connection between area and antiderivatives. If we have a function that's non-negative, just for ease of definition, it doesn't actually have to be non-negative, just makes it easier to see what's happening. Then we like to think about the area under the curve between A and B being the integral from A to B of f of x. That is how we write it. And at this point, it just means area. And then we are about to make the connection that is also very related to the antiderivative. So we're going to define, we're going to define again, right, some partial area function where we're going to say that capital F of x is equal to the integral or the area under the curve from A to x under the curve f of t. And f of t and f of x are just the same function. We're just using a different variable name to help us out because we're already using the x here, so we can't use it here again. It'd be weird. Okay. So like last time, we noted these two things. F of B is just the area under the curve from A to B. F of A is the area under the curve from A to A, which is just 0. Welcome to 21B workshop. Have a seat. There's some handouts. This one particularly is the one we're looking at right now. You might want to follow along. So we're all well and good here. Now the idea is we're going to take the derivative of this function. And the whole point is to show that the derivative of this antiderivative or of this area under the curve ends up being just the function inside. That is the point we're working towards, that the derivative of the integral gives us the function you started with. They undo each other. I mean, well, so integrating, anti-differentiating, it's essentially the same thing. I guess I say when we take the derivative of the antiderivative, we get back to the function we started. Okay, but I will tell you, people will interchange those words all the time because they're very closely related to each other, and we often use them interchangeably, even though they don't mean exactly the same thing. It's close enough that we just did. So we're going to find the derivative of capital F of x using the limit definition. Oh, and by the way, for those of you that have shown up, please do fill out the attendance form when you have a chance. For some reason, for those of you on Zoom, I can't open the link I have to the attendance form, so please do go to Canvas and fill out the attendance form when you have a sec. So limit definition of the derivative, seeing the limit as h goes to 0, of f of x plus h minus f of x all over h, as we've done many times in 21a. Stop me if you have questions or interject, right? Like I'm just like carrying forward like this is all making sense, but if there's something you want me to clarify, I'm happy to clarify it. At this point, we're just looking at this and saying, oh, well, f of x plus h just means the area under the curve from A to x plus h. So f of x plus h is really all of this area here, from here to there under the curve. And f of x is all of this area here. And so the difference between them is this shaded part here, the whole thing. So all we're doing is rewriting this as that's the area of that thin strip from x to x plus h all over h. And now we're going to say something about this. And so I was thinking about this and I felt like this wasn't super duper extra clear to everyone. So I went and wrote up the proof because I think it's worthwhile. You can also certainly Google the proof for the mean value theorem for integrals, but let me show it to you anyway, because it's not too hard to understand and I think it's good to see. So why should it be true that for this thin strip here, there's some point between those 2 points where the area, can you see that? Yeah, where at this point, the height is such that the area under this rectangle, I'm drawing red here, hopefully the red shows up all right. That area in red is the same as the shaded black area. And that is true. There has to be a point where that's true. Here's why. I already wrote this up. I'm trying to go too fast, but there's a lot to get through, so I'm trying to go a little faster. So You already know the mean value theorem. You just don't know it for integrals, but it's essentially the same. The mean value theorem just says if you've got a function on some closed interval, that at some point in the interval, the slope of the tangent line is equal to the slope of the secant line. Or in other words, there's some point where f prime of c is equal to f of b minus f of a over b minus a. Now we're going to do that for integrals. It's the same idea. So here's what we need. We need the function to be continuous on a closed interval. Then we're going to say that there is at least one number c in the interval such that exactly what we want, that f of c times b minus a is equal to the area under the curve f of x, which is exactly, sorry, I just lost my picture here. Keep losing things. Which is exactly what this picture is saying, right? That the area under this rectangle, f of c, the height, times the width, which is our b minus a, is equal to the area under the curve, the integral from a to b of our function. Same idea, just using a and b instead of x and x plus h. Okay. And I think I even wrote it here as well. Right? Yeah, that's the area of the rectangle, the height of f of c. That's the area under f of x from a to b. Okay, so now here's the proof of why this is actually true. So first things first. Since f is continuous on a closed interval, it has to attain its maximum and minimum. Last quarter, we probably learned the extreme value theorem, which does exactly that. If f of x is continuous and on a closed interval, it has to get a maximum value, and it has to get a minimum value. No ifs, ands, or buts about it. So let's call the maximum value capital M and the minimum value lowercase m. That is our function f of x, at least on the interval from a to b, is always going to be bigger than or equal to lowercase m and less than or equal to uppercase m, because capital M is the max and lowercase m is the min. So then we can say the following, and this is what I think is kind of neat. The area under the curve has to be bigger than or equal to the minimum value of the function times the width. Has to be less than or equal to the maximum value times the width. What this is just saying here, and I'm going to draw a picture right here, is that, see that? Yeah, you can see that. Let me draw this in a very easy way to see here. So that's our function f of x, and we're looking between a and b. What we're saying is that that area under the curve from a to b, you're welcome to take a picture, whatever you want. Yeah, go ahead. No worries. So you can always take pictures. I mean, you don't have to record anything because it's recording, and I'll post the recording later. But you're welcome to record if you really want to. The area under the curve is more than the area of this blue rectangle, which is just the base b minus a times the height, which is the minimum value. Oh, the blue rectangle area is exactly the minimum function value times b minus a. And it's certainly less than or equal to this red area here, which I will do this way, which is definitely the maximum function value on that interval times the base of the rectangle. So it has to be true that the area under the curve is between those two rectangle areas. Bigger than the smallest possible rectangle, it's smaller than the largest possible. Cool. That's all this is saying right here. Okay, so then we're going to divide both sides by b minus a, or I should say all sides, since it's a compound inequality. So we've got the minimum value of the function is less than or equal to the area divided by the width. By the way, this is called the average value of f of x, in case you care. Comes up occasionally. And that's certainly less than or equal to the maximum value. Right? Simple, just dividing everything by b minus a. Okay, and then we're going to appeal to the intermediate value theorem. And again, the intermediate value theorem says if you've got a function that's continuous, it just attains all y values between whatever your two endpoint y values are. So there has to be a number c between a and b so that f of c is equal to this value between this lower value and this higher value. right? Essentially, we're saying, here's the lowest value, here's the highest value. There's got to be some C in between A and B that's equal to the actual value that gives you the area when you multiply it by B minus A. Or in other words, there is a number C, so that f of C is equal to 1 over B minus A times the integral from A to B of f of x dx. Or in other words, the result that the area under the curve is equal to the base times the height for some height in the interval. That is, yeah, that's exactly what they're saying. F of C is the average value of the function. But we're going to use that to finish the fundamental theorem of calculus. So that, I know that was kind of a lot. Questions? Go ahead. You go ahead. I didn't have anything else. Yeah.
There has to be some C which equals the number in the middle.
Right.
Because
yeah, exactly.
Okay.
Yeah, it's not like a terrible, huge thing. It's just like, but I felt like it might have been a little hand wavy last time I talked about it, so I wanted to be a little more in depth about it. You probably, I've actually honestly, I've probably never seen it called the intermediate value or the mean value theorem for integrals, just because that's not what I ever, but it's just part of the proof. I've usually when I've seen this proof before, this part is just kind of incorporated in, it's done a slightly different way. Fine. Yeah. Also, there's questions on Zoom. Feel free to ask, write them in the chat. You're welcome to. Okay. So we're not quite done with the fundamental theorem of calculus. So let's go back to the fundamental theorem of calculus. So what this says then is that so as we just said, by the mean value theorem for integrals, there has to be some number C, and C lives between x and x plus h, so that the area under f of C, or the area of the rectangle, that is f of C, the height, times h, the base, that area is equal to the area that's shaded, the area of this thin strip of the rectangle. Okay, that seems right. We just said it twice already, so it seems reasonable. And then we're going to replace this limit with this much simpler limit. You say, oh, well, that's the same as the limit as h goes to 0 of the area of that thin strip. We just said, oops, sorry, you can't see that. Apologies. We're replacing this limit with this limit down here. And the area of the thin strip is just f of C times h over h. No, sorry, it's just f of C times h. And then we're still dividing by h because it's part of the limit definition of the derivative. Okay, but then the h's cancel. And then we take the limit as h goes to 0 of f of C. And I know I said this last time, I'm going to say it again. Since C is between x and x plus h, and h is getting smaller and smaller and smaller, that means this point is getting closer and closer and closer to that point, which means C being between them also gets smushed closer and closer to that point, which means that C is getting closer and closer to x as h gets smaller and smaller. So this limit is equal to f of x. But that shows us that the derivative of capital F is equal to little f. Or in other words, f prime of capital F prime of x is equal to f of x. And so then this is the fundamental theorem of calculus part 1, which says that if you take the, and I rewrote it, I scratched out the capital D there because I'm just not a fan. If you take the derivative of the integral from a to x of f of t dt, you get just the function inside there. And we'll talk about this chain rule version a little bit later because we don't really need to get, we'll talk about it today. We just need to get into it right this minute, but there is a chain rule version as well, which we'll cover shortly.
So earlier you said that we use t as dominant variable, like
right.
Variable.
Right.
I'm still a little confused between the distinction between this type of differentiating and just the actual derivative. Like, what is the difference here? What's the difference between the derivative of a to x of f of t dt with just the actual derivative of f of t?
Sure. Well, so I mean, yes. So here's what I'll say about that. The reason we use this notation for the general antiderivative where you don't have limits of integration is because of the relationship between the antiderivative and the derivative, and the integral and the derivative. So the reason we're using this is because we know that we're about to see, we don't know yet. We're about to see that you can find the integral of a function, the area under a curve of a function between A and B, by taking the antiderivative of that function and plugging in the endpoints, which is the part you probably maybe already started doing anyway, right? Maybe not, you might not have, but that is what we're going to see. That you calculate the area under a curve by anti-differentiating the function and plugging in the endpoints. Top point first, subtracting the bottom point second. And that's actually the second part of the fundamental theorem of calculus. I don't love the way it's done right here personally. I'm going to show you a slightly different way in a second, but let's do that. Unless there's any other questions you want me to address before we do that.
Is f of c equals 1 over b minus a times the integral of a to b, that whole thing,
Yes.
is that basically like the formula form of what we were just talking about? Like there is an a.
Yeah. So we were talking, instead of using A and B, we were using, sorry, where'd you go? We were using x and x plus h. So here, instead of using A and B, we're using x and x plus h instead.
Oh, I see. So it's basically the same thing.
Same thing, exactly the same thing. Yeah. Okay, so I think I'm good here. Yeah. Okay. So I'm just going to point out a couple examples real quickly. So fundamental theorem of calculus, part 1, again, just says that the derivative of the integral from a to x of f of t dt is equal to f of x. And I should point out, because it is worth, or it's not even worth, it's vital that we note that that a is a constant. So it could be like 2 or pi or 0 or whatever, but that x is certainly the variable of interest. So for example, the derivative of the integral from the square root of pi to x of cosine of t squared dt. I'll first point out that this is impossible to anti-differentiate. There is no nice antiderivative of cosine of t squared. There is no elementary function whose derivative is equal to cosine of t squared. That's fine. We don't need it because we're not trying to actually find the antiderivative of it. We're saying that the derivative of the antiderivative of this function is just equal to this function. Now, before we do any more examples, I really do need us to have the second part of the fundamental theorem of calculus to show us how this first part actually works better. So let's talk about the fundamental theorem of calculus part 2, which is the part you're really going to use most of the time. Your teacher, depending on your teacher, might have you do some of this, but not a lot of it. But you expect to know. But really, the reason we really care, well, one of the reasons we really care about the fundamental theorem of calculus part 1 is because we use it to get the fundamental theorem of calculus part 2.
Going to incorporate chain rule into part 1?
They might. They should. I don't know if they will. Some of them will. Some of them probably won't. Yours probably won't. Right. Exactly. So here's what the fundamental theorem of calculus part 2 says. If we know that the antiderivative of little f is capital F, or in other words, I'm going to write it this way. If capital F of x is any antiderivative of little f of x. There's a much easier way of writing that. We could say if the derivative of capital F is equal to little f. Right, that says the same thing. Capital F must be an antiderivative of little f if its derivative is equal to little f. So if that's the case, then we can say the following. The integral from a to b, where a and b are both constants, of little f of x dx is equal to capital F of b minus capital F of A, which most people will probably write as capital F of X evaluated between A and B. Meaning you find the antiderivative, then you first plug in B, then you subtract, then you plug in A. That's what that notation means.
The antiderivative symbol is basically just a symbol we use. It doesn't have anything to do with the integral. It's just an inverse of the derivative.
Right.
Not that this in and of itself.
Right. But I mean, but we use it because of this part right here, because there's this natural relationship between finding the area under the curve and using the antiderivative to do that.
But it's just the inverse of the derivative. It doesn't have anything to do with
I would say it's the inverse, it's the undoing of. Because inverse, I mean, yeah, you're right. But yeah, it's the inverse operation of what the derivative does. Yeah. So why does this work? Well, grab my notes here. I know how to do this. I just want to make sure I don't do it wrong somehow. Because like, where'd you go? I'd written it down and I've lost it. Really, James? Really? Oh, here we go. Sorry, 1 second. This is something that I always am screwing up, so I want to make sure I get it right. So here's why this is true. So let's take the derivative of the integral from A to X of F of T dt. And we know that's supposed to equal F of X by part 1. Right. So we know that if the derivative of this is equal to that, then this should equal the integral from A to X of F of T dt should equal some antiderivative of F of X. Let's call it capital F. And we add on a constant, right? Because you can always add on a constant if you find the antiderivative. Because the derivative of this, that C doesn't make a difference. The derivative of a constant on its own, just 0. Question? Well, how do they go from here to here? I wouldn't say it that way, but you could, I guess, think of it that way. But what I'm really doing is I'm using the relationship. I'm saying, if the derivative of this thing equals this thing, then this thing itself must be the antiderivative. It's more that I'm using this and saying, well, that has to be true because if I take the derivative of both sides of this, the derivative of the left side is certainly that, and the derivative of that side, well, the derivative of the antiderivative must be the function that you're starting with. Okay. And now here's where things are. I just love this next part because it's nice. So we know that if X equals A, then the integral from A to A of F of T dt. Well, if I just plug it in, it's going to be F of A plus C. But everybody here, if you think about it for just a minute, if I ask you what the integral from A to A of any function is, the answer should be how much? Right. Which tells us that C has to equal negative F of A. So then, if we let X equal B, we can say that the integral from A to B of F of T dt, well, if I just plug it into this function here, I'm just replacing X with B. So you get capital F of B plus C, but we just found out that C is equal to negative F of A. So that's really going to be capital F of B minus F of A. And that's exactly what we wanted to show. That is part 2 of the fundamental theorem of calculus. That the integral of the function from A to B is the antiderivative, any antiderivative evaluated at the top limit minus the same antiderivative evaluated at the bottom limit.
Transfer the value of C that we found at X equals A to X equals B.
Well, the value of C doesn't change, right? This C is the same thing, like this and this and this are all the same. We're just saying it's plus some C, but we actually have found it now. It's kind of like, that's not a good example because we haven't talked about that yet. No, it's not a good example, sorry. I don't have a, it's kind of like to say, it's,
Just happens.
it like we're specifically solving for C. We found C, oh, it's negative FA. So really what I should have said here, I guess I should have said, so because of this, we're now saying that the integral from a to x of f of t dt is equal to capital F of x minus capital F of a. That's what we actually just said there. And then one more thing, wait. So then, but instead of using t, we'd rather just use the variable x. So we actually then go back and say is, oh, the integral from a to b of f of x dx is equal to f of b minus f of a. And that is the fundamental theorem of calculus part 2. It's also called the evaluation theorem. It is the part we are going to use a lot when we do more stuff.
So two really good things. The first one is we are allowed to let x equals a and b.
Yeah.
Just because
F is a function.
formula is supposed to work for any x.
Right, it's a function, yeah.
And then essentially what you did with C is you're saying if this formula holds for all x, C has to be negative f of b, capital F of b.
Yes.
And then the second thing is how do you change the variable from t to x at that very last part?
Well, so it certainly, it doesn't really matter what variable we use. If we're saying, right, if I have, I mean, really what you could do is you could do a u substitution later on, which we haven't talked about yet. But basically, if you call, it doesn't matter if I call the function f of t or f of x, it's still the same function. I'm just using a different variable name.
Sure.
Right, right, right. It's kind of like saying the area under the curve from 1 to 4 of x cubed dx should be the same as the area under the curve from 1 to 4 of t cubed dt. Right? It doesn't matter that we've used t's or x's as long as everything else is the same. Okay, so the reason I really wanted the second part is so that now I can really kind of make you believe better, really good sentence there, make you believe better, that the fundamental theorem of calculus part 1 actually does what it does. So let's look at this next example. Where am I? Just put everything everywhere. There we go. There's my example. Cool. So I want to find the following. The derivative of the antiderivative from 2 to x of t cubed dt. Now, the real answer here is that we shouldn't have to do any work. If someone asks you this question, the answer we should just be able to say is, oh, it's x cubed. Because the derivative of the antiderivative of, or I should say the derivative of the integral from a constant to x of some function of t is just that same function of x. That's your f of t. That's the same function, but of x. But maybe you don't feel so much like you believe this. The two does not matter. It is real. So here, yes. So let's do the thing. So we're actually going to calculate this using the fundamental theorem of calculus part 2. So if I want to find the derivative of the integral from 2 to x of t cubed dt, let's actually find the antiderivative or the integral from 2 to x of t cubed dt. So that's going to be, let's see. So the antiderivative of t cubed is t to the 4th over 4. Right, just using the fundamental theorem of calculus part 2. And I'm going to evaluate that at 2 and at x. So now I'm going to plug in the top thing first, the bottom thing second. So do make sure you get that right. It's always the top first, the bottom second. So that's going to be the derivative of x to the 4th over 4 minus 2 to the 4th over 4. I'm going to simplify this just a little bit before I differentiate it. That's going to be the derivative of 1/4 x to the 4th, and 2 to the 4th is 16, and 16 divided by 4 is 4. Great, I'm ready to take the derivative. The derivative of 1/4 x to the 4th is going to be 1/4 times 4x cubed, and the derivative of 4 is going to be 0. Oh gosh, I did. I said x to the 4th and I wrote 4 to the x. Holy smokes, that's terrible. 1/4 x to the, oh my gosh, times 4x cubed. Sorry, oh, brain, good job. Really blew it right at the penultimate moment there. There, that's what we meant to have. 1/4 times the derivative of x to the fourth, which is 4x cubed, not x to the fourth or 4 to the x, minus the derivative of 4, which is 0. 1/4 times 4x cubed is x cubed. As expected from the fundamental theorem of calculus part 1. Yeah. No, because this really is, if you look at this integral here, this is a function of x. The t is it's just a dummy variable. It's just sitting there so we can get rid of it.
We can only, as long as we have this one, we can only differentiate respect to how much area changes of x or whatever way we want to call it.
Yep.
It actually does, we are differentiating with respect to x, it's just
Right.
that, okay.
That's why I've got d dx over here. So someone might ask you to do this, they might ask you to anti-differentiate and differentiate to kind of actually see that it works. But long story short, we don't have to do this, right? If someone's asking you to find something like, I don't know, the derivative of the integral from pi over 4 to x of secant squared of t dt, we could do the work. We could do it the long way, as I would say. But really, we should just be able to say, well, I'm going from a constant to x, so that's going to be secant squared of x. End of story. I do like seeing the work. Wait, can you explain how you got the second step again? Yes. Sorry, by the second step, do you mean like right here? Cool. So what I did was I used the fundamental theorem of calculus part 2, which says that the integral from a to b, or from whatever endpoints you like, of your function is equal to the antiderivative of your function of t cubed evaluated between 2 and x. And then we plugged in and so on and so forth. Now I will point out, in fact, I'll do it in this next one. Let's do it the long way here. So we're going to calculate the long way as well. So if I try to do the antiderivative of secant squared of t, what's the antiderivative of secant squared of t? Tangent of t. So it's tangent, but let's say it's tangent of t plus a constant. Just to actually see. Okay. Just making sure I'm not like going over or something. Of pi over 4 to x. So if I plug in x, I'm going to have the derivative of tangent of x plus c minus tangent of pi over 4 plus c. So I want to observe actually two things here. Thing one, when you do a definite integral where you have limits of integration, you never need the plus c, because the plus c here and the minus plus c here are going to cancel out, which is why you see people not writing the plus c for a definite integral limits of integration. You could, it's totally fine to write it, you just never need it. The second thing is less interesting. Tangent of pi over 4 is what? You know what? I don't care. I mean, it is 1, but really I don't care, because I know whatever tangent of pi over 4 is, it's a constant. There's no variable there. It's just some number that never changes. And I know that the derivative of a number that never changes is going to be 0. This is going to be equal to the derivative of tangent of x, which is secant squared of x, minus the derivative of a constant, which is 0. That's why, to answer a previous question, that's why this 2 doesn't matter, or this pi over 4 doesn't matter. Because when you anti-differentiate a function and then you plug in a constant, you've all of a sudden got a constant. And derivative of a constant is always going to be 0. Cool. So, yeah, we should talk about the chain rule version. You're welcome. Yeah, and also just know you're welcome to come and go as you please. You need to leave early, you need to come late, totally fine. You're welcome. Yeah. Where'd my other examples go? They're all hiding from me. Where'd you go? Oh, there we go. Cool. So The chain rule version is kind of neat. I feel like doing another long way example is kind of the best way to see it. So let's say we want to find the, let's go here. Let's say we want to find the derivative of the integral from, sure, what have we got here? -3 to x squared of cosine of t dt. All right, sure, that's fine. I was gonna do pi, but whatever. So let's actually do the antiderivative because we can. I'm gonna state again, a lot of times if you get asked these questions, the integral is actually something you cannot anti-differentiate. And you're really meant to just do it this way, this short way. But here we'll do it. So let's see. The antiderivative of cosine is positive sine. So this is going to be the derivative of sine of t evaluated between -3 and x squared. And then we're going to plug in the limits of integration. So we're going to get the derivative of sine of x squared minus sine of -3. Okay, the derivative of sine of x is cosine of x. That's how we found the antiderivative of cosine of t. But the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff because of the chain rule. And the derivative of sine of -3 is what? Right. So we end up getting cosine of x squared times 2x. Or the short way of seeing this is you plug in whatever this function of x is for every t, and then you multiply by its derivative. So I'm just thinking of saying, okay, I'm going to get cosine of plug in x squared for t, then multiply by the derivative of x squared. So let's write the general chain rule version of this. It's not too terrible. So in general, here's the chain rule version of the fundamental theory of calculus part 1. It says that the derivative of the integral from a constant to g of x of f of t dt is going to be f of, instead of f of x like before, it's now you're plugging g of x in. So it's going to be f of g of x times g prime of x. And just to kind of make it a little more maybe obvious that it's really the chain rule that you're used to, if you're thinking of this as your capital F of g of x, then your derivative is really capital F prime of g of x times g prime of x, which looks exactly like the chain rule looks. You take the derivative of the outer function, you leave the insides alone, you multiply by the derivative of the inside. It's just that the derivative of capital F happens to be little f. Okay, let's look at a couple more examples. Yeah, we got time. So you can use this to calculate something like the derivative of the integral from 0 to the natural log of x of the square root of 1 plus t squared. Again, the point here being that you can't do this one the long way. And you shouldn't, right? Unless someone is specifically asking you to do a question like this where you find the derivative of the integral the long way, you should always assume that they mean for you to use the fundamental theorem of calculus. You're like, oh, the derivative of the integral of this function is going to be the square root of 1 plus, I'm going to plug in natural log of x. Then I have to multiply by the derivative of the natural log of x, which is going to end up being the square root of 1 plus the natural log of x quantity squared times 1 over x. But couple more situations we might get attacked with here. If I wanted to find the derivative of the integral from, say, e to the x to 5 of t squared over t to the 4th plus 1. Our function happens to be in the wrong spot, right? We're used to having the thing that has x in it be the top limit of integration, not the bottom limit of integration. So what we're going to do is we're going to use the rule that we actually haven't talked about in this class, but you might have already seen, that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Or in other words, if you change the order of the limits of integration, you change the sign of your integral. So we could rewrite this as the derivative of negative of the integral from 5 to e to the x of t squared over t to the 4th plus 1. Hopefully that seems somewhat reasonable to you. And then we do the same thing. We plug in our function. So we're going to get, so I'm going to plug in e. So this is where, well, this one also illustrates something, is that you're going to plug in your function wherever you see t. And there might be more than one t. So here we're going to get e to the x squared over e to the x to the 4th plus 1 times the derivative of e to the x, which happens to also be e to the x. And I suppose if I were simplifying this, I would write this as, let's see, e to the x squared is really e to the 2x times e to the x over e to the x to the 4th is e to the 4x plus 1. So I would probably write this as e to the 3x over e to the 4x plus 1. Actually, I probably wouldn't, but I would know that this is what I was probably going to look for if I was trying to look at like a solution in the textbook. They would probably simplify it this much. And then to make it even more exciting, you can have variables in both the top and the bottom. So for example, you could totally have something that looked like, I want to find the derivative of the integral from x squared to sine of x of e to the t plus cosine of t dt. And just like with regular integrals where you have a top and a bottom, if they're both variables, we're just going to do the top thing rule minus the bottom thing rule. If you like, I don't think you need to, but some people prefer to like break this up at some point in between the two functions. It doesn't have to be in between. You can break this up anywhere you want. So you could write this, if you really, really care to, as the derivative of the integral from 0 to sine of x of e to the t plus cosine of t dt minus the integral from 0 to x squared of e to the t plus cosine of t dt. Does that seem right? I think so. Right? Because the idea here is that I've got some function and I'm going, and it's going to look kind of weird, but it's fine. I'm going from x squared to sine of x. So then if I do this one, the integral from 0 to sine of x is going to be all of this. And the integral from 0 to x squared is going to be all of this. And so then if I subtract the red minus the blue, I should get what I actually want, which is the area from x squared to sine of x. So yeah, that works out. You can always kind of do this thing where if you're trying to find, right, this is one of the rules that's on one of those handouts. The rule being, if you want to find the integral from a to b of f of x dx, you can always write it as the integral from c to b minus the integral from c to a. Essentially picking a new starting place. It's kind of neat. Which then we could say, oh, well, I know how to take the derivative of each of these, right? The derivative of this is going to be e to the sine of x plus cosine of sine of x, all times the derivative of sine of x, which is cosine of x, minus, if I plug in x squared, I get e to the x squared plus cosine of x squared, all times the derivative of x squared, which is 2x. Now, in reality, I wouldn't write this step. I would just be like, plug in sine of x and do the thing for sine. So plug in sine, get e to the sine plus cosine of sine, all times the derivative of sine, which is exactly that. And then minus, and then do the same thing for the bottom part. Plug in x squared, multiply by the derivative of x squared, which is 2x. So you don't need to break this up into this if you can just see it's the top thing minus the bottom thing. So that is how we, if your professor is going to ask you questions or show you this kind of thing, this is most of what we do with the fundamental theory of calculus part 1. We take derivatives of antiderivatives and we mostly just get the function inside the integral. Monday, we will start moving into what's really more the meat of 21B, which is doing all the antiderivatives and all the integrals in the world. So from here on out, we're probably going to not do so much of this fundamental theory of calculus part 1. We've kind of moved past the limit definition of the integral, and we're moving on now to finding antiderivatives, finding area under curve, between curves, volume, all that kind of stuff. And so we're going to talk about, there's kind of like two sides of this coin. There's how like all the physical interpretations, area, volume, surface area, volumes of revolution, all kinds of things. And then there's the methods of integration or anti-differentiation, how to actually anti-differentiate a variety of classes of functions. And we'll talk about U substitution, integration by parts, and whatever other methods we have. And yeah, and it's kind of, I know some professors kind of tend to go in different directions here. Like some people like to do some of the application stuff first, and other people like to do the methods first. I'm more of a methods first kind of person because it seems like it'd be good to know how to do the antiderivatives before we start trying to do the antiderivatives of things to calculate area or whatever. But if you have input as far as what you want to see or which direction you would like to go, you're welcome to let me know. Hey, hi, you kept talking about a handout. Oh yeah, so these handouts are all on Canvas. In fact, let me just show you all on Canvas where they are. Real easy. Assuming I would show you, okay, I was like assuming things open here. You all are welcome to go there. You don't have to stick around. But for those of you on Zoom, I can definitely show you, assuming I get logged in here, where these handouts are. Let's see here. Canvas. One moment, let me get logged in. Cool. Yeah. I don't care about you. Go away. So you go to the class. You just go to the home page or over to the modules. Yeah, I do like going to the modules because then all the announcements don't show up at the top. If you actually click on modules, you don't see those recent announcements, which is fine. Scroll down to the handouts. The handout I was specifically referring to that we were talking about in class today was the fundamental theorem of calculus handout. Yes, I need to download this. Oh, it shows up right there. I didn't need to download it, fine. So it's right there, and it's 3 pages long. You can also look at it over here. It's easier to see. That's the handout I was referring to. There's also the other handout I briefly alluded to was the properties of the definite integral handouts. So if you look at that one, I was alluding to, this property over here, that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. That's the property I was specifically referring to.